So we have a cup filled with water. If I then poke 2 holes in the sides of the cup, ashtray, what happens?
The water will leak out until it's no longer level.
We don't need the until, that's fine. Water will leak out to that. So if I have 2 holes in the sides of the cup, the water will flow out. And the question now is, what would happen if, while this is going on, I were to drop the cup? You can understand why I would actually perform this in class. What would happen if I were to drop the cup? Water's flowing out the sides. I drop the cup. What's going to happen? Adam.
It'll stop flowing out of the cup.
It'll stop flowing out of the cup, but the question is why? What is it that makes it so that it will stop flowing out of the cup? Carol.
The water in the cup has the same acceleration as your gravity.
Everything is going to be accelerating downward at the exact same rate, right? Normally, the water flows out of the cup because it's being pulled downward by the force of gravity. It doesn't have anywhere else to go, so it flows out the sides of the cup. But when the cup is now also going downward at 9.8 meters per second squared, there's no reason for the water to go anywhere but down. So the water and the cup actually go down at the exact same rate. Okay, so I did do a video of it, Asher.
Oh, I was going to say, why can't we actually do that? But
Well, because water goes everywhere. So I did take a video of it. So this is actually a video of, me showing a video in the spring of the year 2000 when I was student teaching. So this is a video of me student teaching. So this is a demo I was going to do, but then I realized it probably wouldn't be a good idea. Because this is a demo with a cup filled with water and 2 holes in it. Video of me showing a video. Everybody go ahead. So right here, water's coming out, and then when he drops it, it stops. There you go. Oh. Do it one more time. So you can see that water stops flowing out, and clearly we determined that's because everything is now accelerating at the same rate, so there's no reason for the water to go anywhere but down. Next. On the upper left, we see a picture over there of, who can tell me what ride from Cedar Point? It's not the Demon Drop. Demon Drop doesn't exist anymore at Cedar Point. It's called the Power Tower. Who has ridden the Power Tower or some Power Tower facsimile? Something of the like. All right. Who's never ridden anything like it before? Who's just not raising their hand because they don't know how to raise their hand? That Tanner. Nice. Very nice, Tanner. Okay. So the Power Tower is a ride at Cedar Point, which hopefully we will all get a chance to ride in May. I'll be applying to the board shortly to get approved for us to go to Cedar Point. Who knows what we've been approved ever at the time, but I don't like to say we're definitely going because it's not my decision. But anyway, the Power Tower. Who wants to describe what the Power Tower is like? Somebody give me a description of the Power Tower. We had a bunch of hints. Okay, who's ridden the Power Tower? Hitu, Power Tower.
Which color?
Go, give me both.
Okay, well, the red one, it just...
He knows the bike color.
The red one, it shoots you up, like...
Just. He used the term just.
You start to upwards, and then you slowly drop back down.
You get shot upward like a rocket. It's important to point out that you are actually strapped to a chair, which is strapped to something, so it's actually safe. It's not just like don't like go on.
And the green one, they slowly raise you up, and then they just drop you and free fall down.
Again, important to point out that you're strapped into something, but you're not really in free fall. Okay, so we're going to talk about what I like to call the down carriage, one where they take you up to 240 feet in the air. You're basically strapped into a chair, and then they drop you. They don't, of course, let you drop into the ground. They do catch you. And it's a way for you to get to experience something close to free fall. It's clearly not free fall because we have air resistance and there's friction from the track and all that stuff. But it's their approximation of free fall. One of the things that I have determined is that they accelerate you downward just a little bit at the beginning to get closer to free fall because there's so much friction. They try to overcome that a little bit at the beginning. Now, what we're going to talk about is an experiment that we're not going to do, and it's not one that I suggest because people could get hurt. If you were, for example, to put a knee on your penny, no? Wow, a penny on your knee. What would it look like if you were to put a penny on your knee and then you were dropped from a height of 240 feet, for example, on the Power Tower? Who can tell me what it would look like? Adam.
It would just float.
Now, it's important to understand that what he just said is actually not correct. It's very close, but it's the most common answer. He said it would just float in front of you.
Well, it would be dropping with you.
Right. So the key here is that you need to say it would appear to float in front of you, right? Because is it actually floating, class? Think about it from the perspective, if you look from the picture, of the person right below you. To that person, that penny doesn't look like it's floating. It looks like it's accelerating at 9.8 meters per second squared directly at you, right? But from the perspective of the person on the ride, it appears to float in front of you. Note, this is the exact same thing that happens on the cup and the water, right? As the cup and the water fall, the water and the cup are accelerating at the same rate, so there's no reason for the water to flow out the side in the same way that the penny appears to float in front of you. Now, let's get to this term, weightlessness, because the penny appears to be weightless, right? It appears to float in front of you.